So I think it's more appropriate to reference this notation not as atomic notation, but nuclear notation. What is the difference between a nucleus and an atom? The nucleus is small. Okay.
Nucleus has a neutral charge?
The nucleus actually doesn't have a neutral charge. It actually has a positive charge. So what's in the nucleus? Protons and neutrons. Okay. Where are the electrons? Outside the nucleus. So an atom is made up of protons, neutrons, and electrons. What is a nucleus made of? Neutrons and protons. So the nucleus is different from the atom in that we don't reference the electrons when we look at the nucleus. Okay? So why would I say calling this atomic notation is a bad idea? In the information that is supplied, either in the symbol, the mass number, or the atomic number, what do I not reference? The electrons. The neutrons are actually indirectly referenced in the mass number. But at no point do I make any notation about the electrons. So this is actually better referenced not as atomic notation, but nuclear notation. And that is typically when this is used. Okay? This is used by physicists or physical chemists, depending on how you want to classify, that are specifically looking at radiation. And radiation is all about the nucleus. What does the nucleus do? And how does that respond and give off radiation? So when they want to look at radiation, what they're concerned about is, number one, the element. So the symbol gives them a big tip off on that. And so that's the biggest thing. It's probably the first thing we see. But then the next thing that we would see is probably the mass number, because we read left to right, top to bottom. Right? So they would see the mass number and say, okay, protons and neutrons, that's a really big number. The larger the number, the more likely it's radioactive. Okay? Why would a larger mass number mean it's more likely to be radioactive? How does it get larger? How do we make the mass number bigger? You have more protons and neutrons. Okay, so if it's a very small number, you have a very small amount of protons and neutrons. Well, why does it give off more radiation if we have a bigger number? What happens when we bring two positively charged species near each other? They repel. So the more positively charged species I put in there, right, the larger the mass number, the more likely I'm going to generate radiation. Right? So radiation is pretty much any element, or at least consistently any element greater than lead, which is at 82. Right? As far as elements go. Okay? Notice what's special about that mass number. 207, it was up 208, 209, 210. Those mass numbers start to get really, 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 really large. So the larger those mass numbers, the more likely we have radiation, the more likely I want to call attention to that if I'm studying radiation. Right? If it's a relatively small mass number like 29, probably like, I'm probably not all that concerned about it. I can still make it radioactive. It is still possible to do so. But we have to do some slight variations off of that. Okay? So this notation is better referenced as nuclear notation, because the only thing we are referencing at this point is the stuff that's in the nucleus. Okay? No reference is made to the electrons, at least obviously. So if we take a look at an example, 2914 Si. Right? What is the element?
Silicon.
Right? How do we figure out what element this is? Okay. So you look at the periodic table of the elements, and what do you look for? Okay. So I heard two answers, both of them potentially valid. We could look for the number 29. Does anybody see the number 29 on the periodic table? Okay, I do see a 29. Well, that's Cu. Okay, so we have to be a little bit careful on what we're looking for on the periodic table. Right? So, unfortunately, Michelle, I'm going to call you out. Why did you say 29?
I don't know.
It's okay.
The number on
Yeah, it's the first number we see. So we go top part of the structure, or top part of the formula. It's 29. That's the symbol I need to find. Because it's on the top, that's where I'm going to look on the periodic table. And if I do so, that number corresponds to Cu, not Si. What? Right. The atomic notation, or our nuclear atomic notation, is different than the order shown on the periodic table. The 29 is the mass number, okay, so it has to do with the weight or the mass, which is actually found on the periodic table under the symbol, not above. Okay. Why would we change that format? Well, remember, nuclear physicists want to know about radiation. They want to see a big mass number because that means it could potentially be radioactive. Why would we put the atomic number on top for our periodic table? Anybody notice any trends? If we read, remember, left to right, top to bottom. We start with hydrogen. What is that number? 1. To helium.
Lithium.
It's organized according to the atomic number. So our periodic table has some kind of trends built into it. It's organized based off the atomic number. So we've placed the atomic number in a place on the periodic table where we can see it and it stands out. Remember, top to bottom, left to right, we're going to place it to the top of our symbol. Okay? Should it always be located to the right? No, that's purely a formatting thing. Sometimes you'll see it dead center, sometimes you'll see it. Ideally, they don't put it on the left because then it could be confused with the nuclear notation. Okay, but sometimes you'll see it centered, sometimes you'll see it to the right. Okay? So the periodic table has a different organization than nuclear notation because there's different people using it. Okay, we're trying to highlight different pieces of information. Okay, does that kind of make sense? Why aren't we consistent? Why not just pick one thing and always present it that way?
Because science is never consistent.
Okay, so we could blame science. Science is never consistent, jerks. Okay, if you go to pay for gas in this country, what do you pay?
It's not consistent, it just depends on the season.
Okay, it can depend on the season, it can fluctuate, but let's just say today. $2.29. $2.29 what?
Gallon. Per gallon.
Dollars per gallon. Right? We drive south significantly. We cross the border. I'm guessing it's different, but I could be wrong. And now we're in Mexico.
Oh, it's
10
more
pesos.
expensive.
Ooh, it's a different currency, and
Math.
they also change from gallon into liters. Right? Why would we change? It's the same thing. Why am I changing the label?
That's how they understand.
That's how they manipulate their currency and their measurement system. Right? So there are different ways that we want to format and organize information. Okay? If you were going to write some information about your elements, right, and you were giving that to me, would you show me a bunch of pictures right now, if we just guessed? Why not? Okay? So you're giving your topic about an element, and you're presenting it to me versus presenting it to your 5-year-old kid or son. I said son again, that's your kid. Brother, sister, cousin, nephew. Are you going to present the same information?
No.
Why not? It's a different audience. You change the audience, you're going to change how it's presented. Okay, so we have to take that into consideration when we go through and look at the stuff being presented in science. Sometimes the audience changes. Just because it's still a scientist doesn't mean that scientist wants to see the exact same information. Okay? So we have to be a little bit careful within our notations. They aren't always going to be the same because you're going to a different target audience. How to make sense? All right, so upper left-hand corner on our nuclear notation was the sum of our protons and neutrons, okay? Which would take us back to, okay, well, let's find that on the periodic table. do we have the mass number on the periodic table?
It's like 28.09.
So for silicon, if we look to where we would expect that mass number to be potentially, you're saying 28.09. What does the key tell you that number is? The atomic weight. What does this say? No. Mass number. Is the mass number the same thing as the atomic weight? No, they're different things. The mass number is defined as the number of protons and neutrons. The atomic weight is related to that, but it's not the same thing. That's why the numbers don't match. They're referencing slightly different samples. Okay? So don't stress about the mass number difference. That's also not going to identify our compound, because I could take aluminum and add an extra neutron to it, or a couple of neutrons, and change its mass. So the mass number isn't going to allow me to identify the element. The atomic number could help. So I could look for 14 as the atomic number, and I would encounter Si. Well, the symbol's there too. Okay, so the atomic number works to identify our element, sort of. The symbol also identifies our element. Okay? But we clearly ran into an issue because several people shouted out, silver. Is Si silver? No. How do you know that? It says Si is not silver on the chart.
No. From prior knowledge or...
It's a prior knowledge thing that you have to memorize. Okay? Just like the English language, we use words to mean things. If you don't know English, it doesn't matter what I'm saying, you aren't going to understand it. Same thing's going to happen with our periodic table. You have to be able to tie the symbol to the name. How would you do that? You look at a table that says this symbol means this name. The same thing with the English language or any other language. Yes?
So if silver or silicone, if it gains a proton, then does it change elements?
So there's an interesting question. If we're at silicon, how many protons does it have? Actually, we'll sort of get to that because that shows up in a little bit. We'll get to that. So the element we know is now silicon, right? And we know it to be silicon because we memorize that the symbol Si is silicon. We have to memorize that. That's what that memory chart of the periodic table is. Okay, so start that memorization process.
If I pronounce it silicone, is that wrong?
Yeah.
Yes.
Okay.
Silicone and silicon are two different things. Okay. Related, but not the same. Atomic number is 14. Well, what did the atomic number mean? It's the number of protons. So this is getting at your question. So how many protons does this symbol tell us we have?
14.
We have 14 protons. So now to your question, what if I add a proton? How many protons would I have? 15. Is it still silicon? No. I've changed the atomic number. The atomic number is now 15. The element becomes phosphorus.
So an element can gain as many neutrons or electrons, but if it gains more protons, then it turns
Yes.
into a different element.
Right? If I change the number of protons, I change the element. If I change the number of electrons or neutrons, I don't change the element. The element stays the same. Okay? Which is an important observation, I believe, for the next slide. Right? Mass number is 29. So what else do I know?
The mass numbers, number of protons and neutrons.
The mass number is the number of protons and neutrons. So 29 equals, I don't know why it's spaced like that. It's a little bit weird. 29 equals the number of protons plus neutrons, which means I can now figure out the number of neutrons because protons were 14. I can now do my substitution in, and I find out the number of neutrons is 43. Oh yeah, that didn't make any sense, right, did it? Okay. We get 15 neutrons. Okay? Make sense? 43 was a joke.
Like, who is teaching?
Who's teaching who? Okay? So that's the information that's stashed in the nuclear notation. We now have access to that, and we can now potentially use that. You're responsible for being able to look at that notation and pull all that information out. Make sense? Okay. What if I now say it has 16 electrons? Which of those symbols will change? So let's box it in. Within that red box, if I say it has 16 electrons, what changes? Nothing. 43 electrons. Nothing. Okay. We've not addressed at all any information within our symbol about how our electrons are located. Okay? Make sense? Okay. So, most of this table should be review, so I'll give you a couple minutes to go through and kind of fill in the table. Where's the location for your electrons, protons, neutrons, the mass, the charge, the symbol, and then that last one's the tricky one. Okay. I believe it was London?
Yeah.
London already gave us a hint on what the protons meant. But now you got to figure out what's going on with the electrons and neutrons. If you got questions at all in trying to reprocess and put that information out there, just raise your hand, I'll come to you. But put it together and see what you can come up with. In theory, you should be pretty darn close. In theory, you should have actually finished a little while ago. I noticed a lot of people were struggling because you're trying to draw on a table. Why are you drawing a table? Because there's a table on the slide. That's why I got to match it up, make it look nice and pretty. Do you have access to these slides? Yes. Should you be drawing a table? Right. All you have to do is have the slides, and then you can write that information in. You save yourself time. Because what will end up happening is we may start moving through questions faster, and if you're frantically trying to write what's on the slide, you aren't actually doing the added value to this. Okay? Just a general thought behind your process. It's up to you if you want to pay attention to me or not, as always. Okay? So let's move to the meaning. Okay? The meaning of protons. London, like I said, already hinted at it, so I might end up calling him out at it, on it, and see if he can push it the rest of the way. What is the meaning of the number of protons?
How much the element, how much positive charge the element has?
We'll get to positive charge in a second, but the latter part of that's the more, I think it's latter, part of that is the more important part. It defines the element. You change the number of protons, it's not the same element. Okay? So I would argue that if we look at protons, these are really straightforward, and they define what element we're looking at. And that tells us the symbol that we need to be writing. Okay? As long as we have the periodic table with us. Okay? What about the electrons and the neutrons? Becomes a little bit trickier. So let's fill in some information with our protons. I'm going to fill in because, again, London was already starting on this. Said it was a positive. So if I looked at a carbon atom, right, just on its own, normal, happy carbon, that carbon atom would have 6 protons. What would its charge be?
Positive? Or wait,
Just a positive? What is the charge on a proton? Positive. How many protons are there?
6.
6. So if you have $1, you're plus $1. If you have $20, you're not plus $1. You're plus 20. We have 6 protons, so our charge would be
6.
plus 6. Okay? Is charge a good thing?
Yes.
Okay. If I walk, or a safe thing, let's try that.
No.
No, charge is an inherently unsafe thing. Okay? Which means everything in chemistry is trying to neutralize that charge. I'm not going to be able to find a carbon atom just sitting with 6 protons because the charge on that atom now is really, really high. How could I neutralize that charge? I would need to add some electrons to it. Right? Well, ideally, how many electrons am I adding to this?
3.
Right? What would the charge be from those 3 electrons?
3 plus 3.
What is the charge on the electron? The electron was a -1. So if I have 3 of them, it's not a +3 charge, it's a -3 charge. What would the charge be on my carbon? A +3. Okay. What if I said instead of there being 3 electrons, there were now 4? What's the charge contribution from the electrons now? -4. What does the charge on our molecule or our atom become? +2. What is our number of electrons changing? The charge. The electrons determine the charge on our atom. Right? Well, those of you probably say, well, don't the protons also contribute? Yes, but the protons are already defined in the element. Once I've defined the element to determine what the charge is, I have to add electrons. So the electrons are largely going to be the thing that dictates our charge. Okay? So now we've got some kind of hints going. What do we think the neutrons are going to do?
Nothing.
Nothing, because the neutrons don't contribute to the charge, because the charge on a neutron is 0. So I completely agree. Neutrons have no contribution to the charge. But do they have no contribution to the element?
No, they help us a mass.
They change the mass. A proton has a mass of 1. A neutron has a mass of 1. Once I've defined my element to determine the mass, I have to know how many neutrons are added into it. Okay? So I would make the argument that our neutrons define the mass. Okay? Kind of makes sense? Okay. So let's go through and take a look at carbon. So this is pretty much straight off a periodic table. Example at the bottom. How many protons are in that structure, or in that
6.
box? How do you know there's 6 protons?
The atomic number is 6.
The atomic number. How many electrons are there? Why are you saying 6? Okay. Remember, everything we're trying to do is neutralizing charge. So our base level, where we should be starting, is making sure there's no charge. So if I'm going to look at a carbon atom, more than likely that carbon atom will have 6 protons, because that makes it carbon, and more than likely it will have 6 electrons to neutralize that proton charge. Okay? That's my starting point. How many neutrons does it have? I think I heard someone say it. Say it again. 6. So it's like the most satanic element. That's interesting. Okay. Anybody know what organic chemistry is all about? Carbon. It's all about carbon and its reactivity. How many of you have heard experiences from people taking organic chemistry? Yeah, everybody says organic chemistry is the worst, hardest class ever. There we go. Now we know why. It's like it's the basis for Satanism. There we go. That's fun. Okay, so 6 neutrons. So what would the mass number be if it had 6 neutrons? 12. 6 plus 6 is 12. What's that say? 12.01. Why does it say 0.01? Is the 12.01 the mass number? It's the atomic mass. The mass number and the atomic mass or atomic weight are different things. Okay? That is all going to come down to what's happening with our neutrons, which we'll look at in a second. So it's a bit of a cliffhanger, so I just want to cause you to shift gears, and we'll do a quiz. The periodic table is not atomic notation. Okay? So we'll put our atomic number, our number of protons, in the lower left. Okay? The 138 neutrons needs to go
Added to the
Top
88.
right.
added to the 88 and then placed in the upper left. Presumably somebody did that correct, so that I don't have to do this math. 96. Okay, so there would be our atomic notation. Why might I ask about this element?
It's important.
Yes, it is radioactive. We have a really big mass number there.
Isotope.
It is an isotope.
Because it needs electrons.
It's Curie's discovery. Okay, it's one of the reasons why she got a Nobel Prize. Okay, it's the source of radium, is what was used, and I think it was actually what was used in Rutherford's experiment as well. So by Curie isolating that, we get Rutherford's experiment. Okay, so sometimes there's logic behind what I ask. Some people picked up on this sometimes. Wow, okay. So isotope, what is an isotope? Remember, protons define the element, and then we said neutrons define the mass. I will notice here I'm saying the isotope, okay? And we're also saying here the type of element. Okay? It is also the mass of our element. Okay? What does that mean? I can have an element with a single proton. If I have an element with a single proton, that is then defined to be, according to our periodic table, hydrogen. If I add a neutron to that hydrogen, I've changed the mass. But the element identity hasn't changed. It's still hydrogen. Okay? But its mass number has changed. Okay? We're all humans, theoretically. We're really good mimics. Thank you. Okay? Do we all have the same mass? No. Okay? So we could effectively be isotopes of humans. Okay? All that's changed is the mass. We're still fundamentally human. Hydrogen with one proton and no neutrons would have the atomic notation shown. Okay? That H, or that 1H. Hydrogen with one proton, well, it has to have one proton, and a neutron, now we'll have 2 for the mass number, because it has a proton and a neutron. Okay? That is still hydrogen, but its mass has changed. Okay? Well, should that change the properties of the element? Okay? If I get thrown at you versus... Sorry, because there's a bigger difference there. Versus Samantha, right?
Yes.
Versus Samantha getting thrown at you. Are you going to respond differently? When you go up to higher and higher speeds, it stops mattering. But if we, 20 miles an hour speed, okay, you're probably going to be a little bit more concerned about me flying at you. Okay? You might be able to dodge Samantha. You might even be able to catch and help her. You're probably not going to be able to catch and help me. Okay? So the mass does change the properties of how it interacts with the world. Okay? That subtle change in mass is detectable enough. And because it has a different mass, we might want to call attention to it as being different. That's where we have the isotopes. And we can say we have hydrogen of mass 2 or hydrogen of mass 1. So I could call it hydrogen 1 or hydrogen 2. And what we're referencing is the isotope, the mass number. Okay? That could work because we'd see a difference in those names. Okay? If it happens to be 2 isotopes that we typically work with or we see a lot of, okay, or they're really important and we want to distinguish them more, we might get a little bit more creative with the name. And instead of calling it hydrogen 1 and hydrogen 2, I'll call it by a new name. I'll call hydrogen 1 Bob and hydrogen 2 Sally. And now I know specifically what I'm referencing. You might laugh, well, that's silly. Why would you call things by Bob and Sally? We made it up. We can call it whatever the heck we want. Okay? It turns out that what we actually call them is protium and deuterium. Don't stress about memorizing the name. It's not important. Why would we call it protium?
Protons. Has more protons.
How many protons does hydrogen 1 have?
1.
1. How many neutrons does it have?
1.
0. So the nucleus only has a proton. So what name do we choose?
Proton. Or proton.
Effectively, proton. We're calling it protium because it's only a proton. What happens when we move to hydrogen 2? We call it deuterium. Well, D doesn't come after P. I don't understand that. Deuce. Okay. Duet.
Double.
Dewubble. Okay. Are all making reference to the number 2. So we come up with deuterium. Okay. Not much better than Bob and Sally, but there is an origin behind why we call them that. Okay. Any guesses for this one?
Tritium. Tritium.
Are you guessing?
Tritium.
Tritium.
Tritium. I actually don't know water with tritium.
Try for the 3. Okay. So if those isotopes are important, we'll sometimes name them differently. Okay. Well, why are we talking about this? Remember, way back when we said the atomic weight didn't make sense. Okay. Deuterium exists, tritium exists. Both of them are hydrogen. What is the atomic weight for hydrogen? 1.01. Why is it not exactly 1?
An electron.
Oh, there's one, it's a protium.
It would be exactly 1 if all hydrogen was protium. Is all hydrogen protium? No. Some of it is deuterium. Some of it is tritium. What is the atomic weight? It takes into account everything. It is the average of all isotopes.
That has to do with that element.
That has to do with that element because it's specifically located in that box. Okay. Can anybody do an average real quickly and be like, you're full of crap, Mike, that's not true? What's the mass of protium? 1. What's the mass of deuterium?
2.
Mass of tritium?
3.
3. If I was going to do an average, I would then divide by 3.
Rhodium's more abundant.
My average says that that atomic weight should be 2, not 1.01. We have an interesting suggestion in the back. This calculation assumes I have an exactly equal amount of each of those isotopes. According to our periodic table, is that true? No. It turns out that protium makes up by far the largest amount of our sample of hydrogen. Okay? It's roughly 99% of all hydrogen.
So it's like the average height, like
So what we're looking at is what is effectively a weighted average. Okay, so let's ignore that question because I think you guys are doing well enough with that. Okay, what we're looking at, or what we have to consider now, is something about percents. Because we could say 99%. Well, what does that mean? If I take a look at a sample, right, a sample of 100 things, and if I get a 99%, that means the one thing I'm observing is 99 of those 100. Okay, that's why we call it percent. Cent for century or 100. Right? So we can use that calculation to help us account for those percentages. Right? So if we look at our percents as a quick example, okay, bronze is an alloy of copper and tin. A sample of bronze contains 79.2 grams of copper and 10.8 grams of tin. What is the percent copper in bronze? Okay. Before we start busting out calculators, what we need to be doing is thinking about our process. We're talking about a percent. A percent of what? What am I being asked for? The percent of what? The copper. The copper in what? Per bronze. Bronze think that's right. Times 100%, and that would get me my answer. Well, do I know the amount of copper in bronze? I'm given some numbers. Right? Those numbers tell me I have 79.2 grams of copper. So do I know an amount of copper? 79.2, awesome. 79.2 grams of copper. This needs to be in my amount of bronze. Well, the other number I've got is 10.8 grams, so I'm just going to do 10.8. No. What is the substance tied to this measurement? Tin. So if I tie in that substance and write tin under here, does that match my equation? No. So I can't put 10.8 in there. I need to put in bronze.
100 grams.
Why are you saying 100 grams?
Because bronze follows it. Because asking.
Okay. I am told that bronze is an alloy of copper and tin. So in a sample of bronze, I know I have 79.2 grams of copper and 10.8 grams of tin. What is the size of my sample of bronze?
90 grams.
Where'd you get 90 from? Okay. We took the two and we added them to each other. And we get 90.0 grams of bronze. Close enough. It's not that dramatic. 90.0 grams bronze. Now I can multiply by 100. Now I can bust out the calculator, run my calculation, and it'll spit out my answer. If we do that math, it comes out to roughly 88.0%, because I'm that good at that math. Okay. Percent copper. How much tin is in 100 grams of bronze? Okay. I'll let you work on that one. The first thing I'll tell you is it is not 10.8. 10.8 was the amount of tin in 90 grams of bronze. Okay. So I want to know how much tin is in 100 grams of bronze. Okay. I'll put some information up. Okay, but with the information we've got, we can pull this off. Okay. I'm saying I'm starting with 100 grams of bronze, and I want the grams of tin in the answer. Okay, because those units are not the same thing, I need to introduce some kind of conversion factor to convert those. In that conversion factor, grams of bronze needs to show up in the denominator so that the units can cancel. Ideally, grams of tin shows up in the numerator so that when the units of bronze cancel, I'd be left with grams of tin. Okay. Do I know the numerical values associated with those units? Okay. Well, that's where we look to the question, okay, or our brain, to see if we know that information. If we've got it, great, this is set up, I just got to plug in the numbers and now I can solve. If I don't, I have to come up with another method. Okay. Do I know how much bronze? Okay. 100 grams. Okay. So I could put 100 grams down here. However, what this is showing is the relationship between the bronze and the tin. If we knew that from the outset in the 100 gram sample, guess what? We would already know the tin. There's no calculation. I have to compare this new sample to an old sample that I know more information about. Do I have an old sample to compare to? What we just did. We know that in a 90 gram sample of bronze, there are 10.8 grams of tin. And I could run through the calculation and I would get the correct answer. Is this the only way to do it? No. There are plenty of other options. Right? This 88% that we came up with was what? That was the percent of copper. Okay, well, I'm trying to figure out the percent of tin. Okay? How could I figure out the percent of tin?
The difference
Difference
of 88% from 100.
from 100. Why'd you pick 100?
Because
There's only 2 elements in it. I know that 100% must equal the percent coming from my copper plus the percent coming from my tin. So I can solve that the percent of tin is 12%. So given a 100-gram sample of my bronze, I could go through and say, or multiply then by 12%. But if I multiply by 12, I'm not going to get the right answer, right? Right? Okay, so we could go through and say 0.12 or 0.12. Why are we doing that? This percent symbol doesn't want to show up in the answer. How do I get that percent unit or symbol to disappear? What does percent mean? What does per mean? Divide by cent. 100. What is 12 divided by 100? 0.12. Okay. We'll get the exact same answer either way we stack this. Well, but 12 and 100 are different than 10.8 and 90. Yes, that's why it works. Okay. So depending on what you see when you go through and solve, okay, whichever pathway works for you is fine. Okay, when we go through and talk about how we solve questions, I will talk about a single pathway that I see that I think is most apparent and is most translatable across the entire course. That's why I went with the first example. Okay. The second example, believe it or not, is how I would typically do it, but that's not translatable across the rest of the course. Okay? So it's all a question of finding what works for you. The other part of it is what consistently works. If I flip a quarter in the air and you call heads and you're right, does that mean the next time I flip a quarter it's going to be heads? No. Just because you're calling heads doesn't mean you're consistently right. Okay? What I want you to go through and do is find the process where you look at the quarter and see both sides of that quarter are labeled as heads, so when he flips it, it's always going to be heads. That's the process I want you to follow. Okay? How do you know that that's the process you're following and not, say, one that's blind luck? You got to do it. How many times do you have to do it? A lot of times. This is the practice that comes into this. You should be practicing these questions. Just because you get it right once doesn't mean you're going to get it right again. Okay? I would recommend for every question type you do 3 questions. If you're consistently right in those 3, you've probably got it down. If you're not, do more. Make sense? Okay. How does this tie back to what we're looking at here? Okay. We run into our averages, okay, which is a way of looking at a percent. If I have a sample of 100 atoms of hydrogen, protium makes up 99 of those. Okay. Deuterium makes up half of those. Tritium makes up the last half. How do I factor in those amounts? Okay, well, I could go through and say, well, 99 were our protium out of 100 sample. Okay, I'm not going to like the half values, so I'm going to switch that. Let's make it 98 were protium, plus 1 was our deuterium out of that 100, plus 1 was tritium out of that 100. Now when I go through and do the calculation, I've accounted for the weighted, the percent abundance behind each of these. How do I know I did a percent?
Divided by a whole.
Well, I'll kind of accept that. We divided per 100 cent. That assumes the sample I was looking at was 100. So that means the only time I can do this is only when I look at 100 things. Okay. Let's take a look at your grade. Your grade can be determined based off of percent. That means in this class there's only 100 points? No, there wasn't. Okay. There's something like 600 or 700 points. Okay? It's whatever the total sample size is. Okay? So this method works, but it doesn't allow us to look at a percentage and extrapolate to everything. Okay? So let's clear this away. And let's take a look again at our sample where we said 1 plus 2 plus 3 divided by the 3. Remember I said in this process, we assumed equal percentages. Well, where in that do you see the percent abundance of each of those? We're like, what? I don't see any percents. That's because it's not there. Okay? At least not obviously. So let's do some math. This is really the same as saying 1 over 3, right? Plus 2 over 3 plus 3 over 3, right? Everybody agree with that? Okay, what was the mass for the first one? What was the mass for the first one? 1. 1 times 1 over 3, right? Plus, what was the mass for the second one? 2 times 1 over 3. Plus 3 times 1 over 3. 1 over 3 is equal to what? 0.33 plus 2 times 0.33 plus 3 times 0.33. This is the same as 1 times 33 over 100. Like, oh my God, this is so much work. Yes, I know. Work with me here. You don't have to write it all down. Whoops. What is the word for this description here? That is 33 per 100, also known as 33%. Within that calculation that we started with, 1 plus 2 plus 3 divided by 3, the percent was implied. Okay? I don't want to imply it because under most circumstances, it's not going to be implied. It would be nice if I had the example right there, but it's not. Okay? So I'm about to delete this. Okay? So everybody's laughing, so let's pause and let's walk through that equation down there. To come up with our average, we took our observed mass times its percent, plus the next observed mass times its percent, plus the next observed mass times its percent. Okay? That's how we calculate an average. Okay? What you're used to seeing is this one up here, because if they're all equal, it's already factored in. I don't have to worry about it. But if they aren't all equal, I have to have the flexibility to change those percentages. Right? So let's take a look. So we good? We got that formula roughly ballpark nailed down. Ballpark. It doesn't have to be like somewhere left field. Okay.
In the ballpark.
That's all we needed. Gallium has two isotopes. Gallium-69 with a mass of 68.926 AMUs. What's an AMU? Who cares? Don't worry about it. It's some arbitrary mass unit. 60.11% abundance. And gallium-71. What is the mass of gallium-71 in AMUs to 4 digits? Oh my God, that's a lot of information. Okay. So let's breathe a little bit. We're talking about two isotopes, okay, with a bunch of numbers. So I'm going to simplify this and say gallium-69 is A. Gallium-71 is B. So gallium, I know it says calcium, 69 we said was A. What do we know about gallium-69? The mass is 68.926 AMUs. What else do we know about A? Its percent is 60.11%. What do I know about, was it gallium 70? 71? Which we said was B. What do I know about it? Do I know its mass? No, why not? That's what you're told to solve, so it probably wasn't given to you in the question. Okay. Do we know its percent? What do you mean yes? Elaborate. Okay. It is not directly given to you in the question. However, we know that there are two isotopes, which means if I add up the percentage of both isotopes, it had better equal 100%. Do I know the percent of A? Can I figure out the percent of B? Yes. I can say 100 minus 60.11 gets me 5% of B. 39, right? 89, thank you. Percent. Okay. I still need to solve for the mass. Okay. And in particular the mass of B. Was there an equation that related the mass of these two substances? That we literally just talked about.
The average?
Okay. Looking at our average. Okay. So our average mass, we'll just call it average mass, is equal to what?
The observed mass times the percent.
Okay, our observed mass of what?
The 68.926.
Okay, of A, 68.926. Times what?
60.11.
Careful. It's not entirely wrong. This is 60.11%. Do I want the percent showing up in my answer? No. How do I get that symbol to disappear? Divide by 100 or shift your decimal. I don't recommend shifting decimals, but if you do it consistent, there's nothing I can complain about. Okay, that's it? That's now the average mass?
Negative.
Okay, what else?
68.926.
Times our 60.1. The 68.926 was what?
The mass.
The mass of A. Do I know the mass of B?
No.
No. Okay, so let's just say B, because I don't know what that is yet. Times what? Its percent.
39.89.
Right? So I have an equation and an unknown. I just have to solve for B. What is the average mass? That would be a percent if we said 39.89, so that can't be the average mass. Well, the average mass is if we do this calculation. Can we do this calculation? Why not? I don't know what B is. Okay, so then the average mass must be in the question. Well, I use 68.926. I use the 60.11.
Next question.
Where is the... What are you pointing at, Lily? Why are you pointing at the periodic table? The periodic table has the atomic mass, which we said was the average mass. If you have a periodic table, and because you're a chemist, you do, you know what the average mass is. You know the average mass for gallium is 69.72. Why is it not explicitly stated in the question? Because you should know that the periodic table gives you the average mass. Can you solve for B now? Yes. Okay. That one I can't cheat on. I don't know the answer to that one. And yes, the last time I spit out 88.0% was because I cheated. Okay. Someone want to tell me an answer they get when they crack that out? Because a lot of people like to know the answers. It's now just doing algebra, shifting things around. 70.992 AMUs. Can we get a second confirmation? Or else I don't have a calculator. Might be a good idea to bring one. Okay, particularly if you're one of those people that are like, I want to know what the answer is. You should have a calculator. Does no one else have a calculator? We're just going to leave it at that. Just want a confirmation that 70.92 AMUs is our answer. We don't want to trust one person. That's awful.
I trust you.
Is it in the right ballpark while people are thinking about that? Okay. A had a mass of what? Or isotope A was 69. The mass was just slightly higher than that. B was isotope 71. The mass we're getting is just slightly under that. Sorry, not higher, under. So ballpark, it seems reasonable. Still nobody?
7.92.
Okay, so we are getting a confirmation of the 70.92. If you're not getting that, talk to me after class and we'll confirm and make sure that you can get that. The 59 is definitely a big mistake in how you're entering it.
69, so I'm close.
69.72, you're still going to be a little bit off. I think that's probably just your direct average.
70.9165.
So we've got confirmation that our answer is 70.92. If you're not getting that, you're making a calculator mistake, talk to me and we'll get that fixed. Okay? After that, what we would do is then move into chapter 5. So we end up skipping a significant section of chapter 4. Yeah, I still got time. I see where the clock is. Okay. We'll end up skipping the second half of chapter 4, which is a bit of a beast, but that's probably where we'll be starting mostly on Tuesday. So read ahead in that and be prepared to ask questions. We're done at 45, right? Yeah. So, periodic table. What do we have on this projector slide now? The periodic table written by somebody on an acid trip. Right? It does kind of look like that. These are different organizations, the periodic table. Right? We don't have to settle on one choice. The reason why we use the one up on the boards or on our walls is because those are the most neatly organized. Okay? They call attention to the biggest facts that we want to use. These ones change the organization of that information because we're trying to call attention to a different feature of the periodic table. Okay? The periodic table is not an absolute. There are variations behind it. Okay? Some of this is kind of come back to how we classified the elements, and this will be the slide that I kind of stop on. Initially, 1830s, they organized things by triads. Why would we pick triads? Anybody in this class have any kind of religion background? Any at all? There's like the Father, the Son, and the Holy Spirit, which is 3. Science has a hardcore root back in religion. They saw 3s, and so they assumed that it was tied back to religion, right, and the existence of God, and we were trying to understand and better reveal that information. Why did they see 3, but they later then moved into 7? Okay, or the sets that we have up here that we don't really see 3. Why did they only see the sets of 3? There weren't that many elements discovered, so they could organize them by groups of 3. Okay, that's where it came from. It then jumped up into, when they had more, sets of 7, okay, which they called the law of octaves because of music. That's where I'll end that discussion because I'm not good with music. Okay, but that's where we'll pick up on Tuesday.